because the bottleneck isn't compute, it's energy. And that's the basis of the world model almost, right? To judge energy, judge failures, even though I know we're doing simulations now. But if you think about it, NVIDIA is doing the same thing. They're basically building what we're teaching, right? They might have their own proprietary things, but really the only difference is they have a closed model structure with CUDA-Q, and we recommend open, right? But when you look at it, including what's going to be basically compute in the future, which is quantum, what they're building, we're teaching. It's exactly the same. So I'm going to put that in the chat and stop sharing. And let you kick in now, Daniel, because as we spoke about before, we pivoted a little bit because it was going to, oh, I got to let in people, sorry. We're going to have to pivot a little bit because I agree with what you're saying or what you said, that with just 3 GPUs, it's going to be hard to get a variance of data enough to predict a failure, right? So we're going to have to simulate it, right? With a digital twin. And I know I put a module about that in the Discord. And basically what I'm going to say before I let you loose is this all fits in a pattern, right? We start with the math and the theoretical background. I was in class today and he was going over linear algebra and statistics. It was awesome with like box plot, scatter plot, or whatever. Then this is the applied version of that, right? Where we're going to have a model, and then put that model back on the Nano via Edge AI. Then as we move on to the fall with the linear robotics program with Dwayne Joseph, go deeper into the language of robotics, right? And then that capstone will be a hybrid quantum classical computing platform. So everything fits in place, everything goes as we move along. Go for it, Daniel.
Yes, thank you very much. So I'll just share my screen. So let me share screen 1. Okay. So you can see my screen now. So first thing, just for the sake of the project that we are doing, I've created a repository just to give you so it's a very simple. I'll just show you how to use so that it's something that if you follow it carefully, we'll be able to build everything from scratch. Like Nolan has said, the first thing you need to understand in first case for your project, before I move into teaching you about quantum computing, which I've prepared a lecture for, which will take me like 40 minutes, and I'll try to do exercises in the NVIDIA, those NVIDIA exercises, so we'll do it together in this period. So just you need to understand the first case, like we are trying to point out, is why a digital twin. So you need to understand that. So this is the repo which I've created. Everything is very straightforward, step by step. I have made sure, so if you follow it step by step, you'll be able to fork the repository. If you know how to create your own GitHub repo, you fork it, you go there, you follow. I've written scripts that you just need to run. So the first thing is how to use this repo. I will teach you. First thing is, once you come to the repository, you fork it. It means you create your repository. You click this fork, you fork, you have your own. Fork is like having your own copy of the repository. So you have your GitHub account, create your repo, do that. Then you can clone it. I don't think, how many of us, which operating system are you using? Like, I just want to be sure because it's advisable you're using a Linux. Huh?
I'm using Windows.
Okay.
Windows. Is anybody using Linux? I'd be shocked.
Okay, so it's you can use Windows, but you will need to install WSL, which is the Windows Linux subsystem.
Ooh,
More,
yeah. Yikes.
yeah. So
Yeah.
you need to first of all you need to know how to set up virtualization on your system if you go to your BIOS. So I think I also need to create a tutorial for that. But it's advisable that if you can dual boot, like me, I dual boot. I have both Ubuntu and Windows running on my system, so partitioned. So I have Windows on one of the SSD and Ubuntu. So this is favorably designed more for a Linux-based system. I'll try to adapt it to see how we can do it for Windows also, because it also can do it because as you can see there are .sh. Windows will run with .bat script. That's bat script. But this is .sh, which is for bash shell. So you can run it on Windows if you create the subsystem on your Windows. So first thing, you need to know, why are we creating a digital twin for a data center? In that case, the first thing is, we discovered just by discussing that if you check a real data center, when last did you hear a data center failed? Means you will not have scenarios of failures. So a digital twin is like the word twin, is first of all, it's not just a 3D model. It's not just a 3D or CAD model. It must have situation awareness and physics constraints. So it must replicate the real world in such a way that you can have diverse behaviors. So the reason for the digital twin is because it's possible for us to simulate what failure will look like, and we can learn from there. Because if we rely on the real world, it will be almost impossible. Imagine now you want to teach an AI model to learn what a car crash is, and you are depending on just data from the real world. So you might not see the frequency of crash, of car crashing, the physics, the impact on the structure of the car, the scenario that means that the car has crashed. So it is always good. So data twins are help to simulate scenarios that don't really occur, so you can have diversity from a diverse set. So it is like a twin of the real world. So it's not just a 3D model. It's also have the physics defining the system. So
Hold on, Daniel. Hold on, Daniel. Is everyone clear with this? This is very, very important.
What do I have to download again?
Sorry, come again. I didn't hear you.
What do I have to download again?
What?
He's asking, what does he have to download again?
For it, like downloading, to what sense?
For Windows, so it could run.
Okay, you're running on Windows currently, right?
Yes.
Okay, so if you go to
And sorry, my chat is acting up too. I can't answer the questions in the chat. I apologize.
So if you go to your
I was like, I was going to ask
if you go to WSL, just go to your Microsoft Play where you get your Microsoft applications. So you look for WSL, but normally before you can do that, you will need to set something on Windows, which is on or off. You need to enable hyper visualization. Okay, so now that's another. We've had our first constraint. So first, your hyper. It depends on which machine are you using currently, and what's the name of your laptop. So every laptop has different way they boot into their BIOS.
Okay.
For me, I'm using MSI. So when you start your system, if you are tapping F11, hyper visualization means that you want to run a virtual machine on your system, so that you can be able. So if you don't enable it from your system, it's not going to be able to run the Linux terminal. So there's a setting. I think I'll just boot. I should I should have boot into my Windows, but let's just stay. So I will give you I will send you the file on how to enable that, because we're not going to do the project now because it's a bit long, but everything is step by step. What we want to focus now is on the quantum mathematics. But I just want to show you a walkthrough of what. So first thing is, we'll come to that hands-on. So we need to understand what is a digital twin. So we say, imagine you manage 5,000 servers in a data center. One of them is, so digital twin helps to simulate failure. So you can have that real. So in this case, I have uploaded a digital twin from the NVIDIA assets, which we will look at. Then we are going to put them on the, so this repo, when you fork it, this one you can do this with your Windows, but you will need to make sure Git is installed on your Windows. How many of us is familiar with Git?
I am.
Quite a few.
Okay, so who has a GitHub account?
I do.
Okay, so if you have a GitHub account, you can also collaborate with your teammates. Have you forked a GitHub repository before? You know how to do that? Anybody?
Yeah, I've done that before.
Yeah, so that's what you would necessarily. So you go through all this. Like I said, if you see the so this is why are we using NVIDIA Omniverse? Because it has the USD. So if you have followed your tutorial, that's what we call the universal scene description. So it gives a 3D visualization of a digital of the world. We will go through this here.
Go ahead, Omar. Go ahead.
Cool. Yeah. So I'm on your GitHub and I'm trying to find the repository. Is it public? Or
Yes, it's public. It's public. So just
okay.
let me put the link on the it's good one, nice one. I like the so like I said, I will send you the repo. I think I put the repo on the Discord channel.
Okay.
But let me just put it on the chat.
Please, also. Thank you.
Yeah, that's a good one. Thank what is that? Just a moment. So let me put it on the chat. I hope this chat is enabled here. Okay, good. So that's it here. So that's the repo. So it follows step by step. But for now, I've not pushed the virtual machine because I just got the rotor. My rotor space increased to 1. So I've not pushed in the virtual machine. I mean, in the cloud, it has the NVIDIA SSD, everything there. So you have to follow everything step by step, and you have to run it on a Linux terminal. I'll try updating the repo to also be useful for Windows, so you can use Windows.
We had a Linux workshop, but ran into some technical problems, so we couldn't finish it all. But they should be at least familiar with Linux.
Okay, so yeah. So I'll do that also just to but for now, I just want to make us understand, the first principle why we are doing what we're doing, so that it doesn't look you're just telling you to do tutorials, because everything here is very easy to follow up, step by step. You source, you do you're just following up. In short, it's almost like once you follow the repository, you're just doing the Python script to train the model, everything. I've written everything, but I just want to make sure that there's no lagging. You understanding why? Because it's good you follow through, then you ask questions. So the thing is just be curious. That's the way to learn. And because it's a very complex project, and it might take you a lot to do it. So, but just be curious, ask why. There's a lot of scripts I've written there. And so that's it. So digital twin that we are using. So let me just show you just so I just want to show you how it looks like. It's not going to load. very well because my system is going to lag, but I just want to show you what the virtual environment looks like of the rack and everything. So you can see, but you are going to have it available on the cloud just in a day's time because I'm going to push it this night. So you can follow through. Okay. So this is the Omniverse environment. This is a blank stage. So if you've been following the workshop, a blank stage, there's no asset in it. So you can easily open an environment which you can use here. For me,
Excuse me, is there something on your screen? Or you?
Yeah, Daniel, is just sharing something.
Yeah,
It's
yeah,
not coming
you're
through.
not sharing your screen.
sorry.
I thought you were building up the anticipation.
Sorry about that. I've been just doing stuff here. Sorry, I'm just a moment. Let me share the screen. I was wondering. I said, oh, okay. So now, can you see my screen? Can you see the terminal that I just ran? Yeah.
Yes, you can see it now.
Yeah.
Okay, can you see? So the terminal, I'm trying to run it just so you can have a visual look of what you're going to see. So this is like the Omniverse environment with the stage. And this is the asset that we're looking at. This is the data center which I've been built. So the reason why we are using the cloud is because some of you won't have the GPU to run this simulator because it's very heavy. I'm using a high-end GPU, 3070, but yet it doesn't run very well. So you can see it's very slow. I'm just trying to open an asset and it's taking so much time. But that's why I'm going to push it to the G Cloud, which I'm going to do. Then you have to, after this lecture, you have to follow step by step the GitHub tutorial, which is here. I don't know if does that make sense. So that's just giving you an idea. So in that's the data hall will be available there. Okay.
What was the script you ran to get here again? I think we might have missed that part.
Sorry, come again.
You ran a script to get to this place, correct?
Yeah, that is already embedded in the tutorial. So don't be too. It's already embedded. It's part of the it's already inside the virtual machine.
Okay,
that's
cool.
the script. Let me show you just to correct you. It's the it's what started this thing. So if you look at this is the hall we're using, this full. This is if I load it, so you see that it's going to load the data center. This is data center that you're going to use. Can you see it? Can you see it? Yeah. So this is which is so you can see it's already showing in my NVIDIA distinction that I'm already used 5.7 and it's showing red. It's running out of RAM as I'm running it local. So that's why we need to run it on the cloud.
Correct.
So that you all can have. So this is the data center. This is not just a 3D model. This is also have racks and all of them have physics. If you have learned how to use the Omniverse, define the physics, there's a lot of things in it. The OmniGraph, define the assets, make them available. So this is data center that we are going to be working with. So you can see there's a lot of things here. There's rack, there's this, there's on, there's off. So we'll be training it what we call headless. Headless means when you are training, you will not need to be visualizing it, the 3D scene. So you run it without it, but it will be running the physics at the background. That way you don't run too much computational costs. Everything I'm saying is in the repo with it. So we are going to do that later. So I'm just trying to make sure you understand the whys before we jump in. Okay. Having said that all, any question, please just ask. No foolish question, just, So
I'll
this
place them in the
repo,
chat.
yeah?
I'll
Yeah,
place
just,
them in the chat. Yep.
okay, yeah, good. So this report contains everything that you need. So for today now, because of Lawrence, Sir Nolan told me that you guys are doing, NVIDIA is going to come and they want you to understand quantum computing. So I just prepared a quick note on quantum computing, and we are going to walk through the example. So this quantum computing currently is not part, I didn't do anything quantum computing in the project. The project is just purely, it's purely a digital twin with a data center environment. You deploy on the cloud, you train let me just show you some of the README so you can see. So before how you use this doc, make sure you read all this README inside this documentation. So GCP concept, synthetic data, what does synthetic data mean? Why we see, so you can see there's a lot of information. And we are training it using transformers. We're using the transformer architecture and not just the conventional. So this documentation is what you must first read to understand the theory behind everything we're doing. Then you start working with the code base. So for the repo, make sure you read the documentation. In the docs file, read everything. There's 1, 2, 3, 4, read them. You will get an understanding. It's very self-explanatory. So just in case you have any question, you hit me up. So now we'll just go into the quantum computing so that we can solve there are 4 exercises that were there, and that's what we're going to do together in the next 30 minutes. Because it's yeah. So first of all, what is quantum computing? You need to understand. So in normal classical digital computing, we have 1 and 0. But in quantum computing, we have what we call qubits. That means a state can be in both 1 and 0 at the same time. And this is so that you can fasten the process. So it exploits the laws of quantum mechanics. So it comprises of 3 major things, which you must know is superposition, entanglement, and inference. And we're going to understand what that means. And what superposition means is that the first thing is that in normal digital computing, you can either have a 1 or a 0. But in quantum computing, a state can exist as 1 and 0 at the same time. So there's a probability of it being a 1 and a 0 at the same time. So that gives it a kind of more like a kind of quantum parallel processing. Then we have what we call entanglement. Entanglement
It's like a penny. It's like a penny spinning, right?
Yeah.
Right.
Yeah, exactly, sir. So, but in case of entanglement is a state where one of the states of the affects the other. So we're going to look at those. So there are some key things you're going to need to understand in classical bits. So in classical data bit, you can either have 0 or you can have 1. But in quantum, instead of just being 0, it can be simultaneous, just as you can see stated here. So now we have a qubit, which is what we call it. So we'll do the exercise quickly. Then where you have a qubit, the probability of a 0 and the probability of a 1 is defined by this. That's to determine the state. So alpha and beta are called probability amplitude. And you know, every probability, the sum of every probability must be 1. For example, now the probability of sum of all the possibilities of an event will sum to 1. For example, if you have a coin probability of a head and a tail. If you add the probability of a head, probability of a tail, all the events happening, it should sum to 1. So the 1 is the sum of every probability. So it means that there's a probability of it being a 0 or 1 at a particular state. So I hope that is kind of clear. So like I said, get a key. In classical bit, you can either be 0 or 1 at a time. But in quantum, we have what we call qubit. So the superposition means it can be either 0 or 1 at the same time. So there's a probability of it being a 0, and a probability of being a 1. So that is can you see my screen?
Yes, if you're showing quantum superposition.
Yeah, so now quantum superposition. So now this sign plus, when you see this sign, if we go to the exercise, you will see it when we start doing the playground. This sign plus actually means there's an equal probability of a 0 and 1. And the phase difference is 0. You will see it in the Bloch sphere when we try to draw it. So alpha is 1√2, because alpha is always, look at this sign, alpha is always the coefficient of this. Beta is always the coefficient of the probability of 1. So if you multiply into that square, into that bracket, you discover that both alpha and beta are the same. But if you multiply into here, you discover that alpha is 1/√2 and beta is minus 1/√2, because if you multiply into, you will get that. So it means that both states gives 50% probability of each. And how do you know the probability? The probability is defined by this equation. Let me show you the formula. It should be a bit down. How did I do that? So when we finish this, we'll go to the so now let's understand. So in the single qubit, so we'll go to the exercise now, and let me split screen. Okay. So I will just go to the, so if you can quickly, let's go to the single bit exercise so that you can go do it together with me. I will share the link now. The first exercise, that just to see that one. So this is the link. So this is, I want you to get it because I believe they might want to test your understanding of these qubits. There's a playground. So that's the first. No. Did you see the no? Sorry. So that's the one. So click that link so that we can do that together. The link I just sent. That's the first exercise.
Oh yeah, right.
Okay, so you all see that can you all see that this quantum gate visualization?
I can see it.
I can see it too.
Yeah, good. That you can see that. Okay, can you see my screen clearly?
Yep.
Yeah. So now, just like normally in normal cases, just to explain, let me go to the original note. Okay. So this is when you have a single bit. So in this case, now we have 0 coming in. So I want you to look at this thing. So there's the S gates. These are normal gates. So when you are building your circuit, just the way in normal digital circuit, you have NOR gate, AND gate, XOR gate. If you have AND gate, if you have 1 and 1, it's going to be 1. If you have 1 and 0, it's going to be 1. If you have 0 and 1, it's going to be and if you have 1 and 0, it's going to be 0. If you have 0 and 1, it's going to be 0. So if you have 1 and 1, it's going to be 1, because AND is almost like a multiplier, more like a product. Then if it's OR, you have 0 and 0 or 0. But now in this case, you have X gate, which is the quantum knot. So what it does is that it flips. If you introduce a 0 as an input, it's going to change it to what? A 1. So we'll try that and see. Let's see what that means. If I put in an X, this is coming as 0. What did you notice? It flipped from 0 to 1. Did you see that? So let's do that again. Look at the green arrow. The green arrow is telling us now what is the state of the gate. So in quantum physics, it's not just 0 or 1. It can either be 0 or it could be 1. But for this simple one, if you apply an X gate to an input of 0, that means the qubit is at 0. If you apply just an X gate, it flips it to 1. You see?
Yeah.
You see that? Makes sense. So let's go a back step again. So the output is a 1.
Is everyone clear on this?
So the S gate has this matrix of 0, 1, 1, 0. Does everybody understand this? Good.
Jonathan's on it.
Yeah. So now for the Y gate will sweep, will give, if you put in a 0, yeah, it's going to give, look at this matrix. I wish, let me look for a whiteboard. There's this free one. No, so paid ones. Yeah, this is good.
Oh, I didn't know Canva has one good.
Yeah.
I get them for being a nonprofit.
Hell, I think. Right then. So for the X gate, this is the S gate. This is the matrix that defines the S gate. You have 0, 1, 1, 0. So when you are putting in a 0, it's almost like you're multiplying it like this. And at the end of the day, you will get a 1. If you put in a 1, it's going to flip it to become a 0 in that case. So that's just what you need to understand. So you need to know that. Then look at the Y gate. The Y gate is defined with this.
So are these gates just like a matrix? Is that
Yeah,
what I
the
mean?
matrix.
Yes.
Exactly.
Okay.
So you can, I will share this note with you. And you know what who knows what an imaginary number is? Like I, or some people use I, some people use J.
Yeah.
So I as imaginary. And you know that I is the same thing as square root of -1. An imaginary. But that's by the way. So this is I.
They're just showing off now.
No, sorry. So this is I. So this is just 1. So when you put in a 0, it gives a 1i, and that I means is actually a phase factor, but in the magnitude is still 1. So let's try it in this Q gate. So if you put a y, it will still be 1, but there will be a phase difference, but it's not visible. It's just going to add to the phase factor. But the Bloch sphere will not show that phase factor, except it becomes aggregated. So if you put in y, you see it still changed to 1. Makes sense. So it's if you put in 0, it's going to give you I1. So it's still 1, but that I is just showing a phase which doesn't capture in the Bloch sphere. So oh, so that's it for that. Now, these gates are things we need to understand very well. Then I'm going to move to the next one, because so you have to play with those stuff and understand the math behind it. So the next one is the Z gate. What the Z gate is, it leaves 0 unchanged and flips the phase of 1. So this is the matrix of the Z gate. 1, 0, 0, minus 1. So if you bring in a 0 into it, it's going to leave it unchanged. If you bring in to this, it's going to be 0, 0, unchanged. 1 times 0, 0 times is 0. 0 times 0, 0 minus 0, 0, unchanged. So if you put in pass this as an input 0, so let's try that for the Z gate. Unchanged. You didn't change it. Does that make sense? But I don't know why this playground you can't change the value of y. I don't know. It's very messy. It's crazy. But there's a way to manipulate that. If you want to get to, who can tell me what we can do to make, let's say we want to put, because now this playground doesn't allow us to put in 1 as a qubit. So who can tell me what I can do if I want to pass in 1 to Z to see what it will look like? What can I do? Let me test your understanding. If I want to pass in a value of 1 to Z, what can I do in this circuit diagram? Because the playground doesn't allow me to change it to become 1. So I want to pass in to see how, when you feed in 1, how it will affect, what am I going to do? Anybody has any answer?
Do you need the X gate?
Thank you. Correct. So if I put in an X gate, it's going to flip it. So it's almost like what is coming out now is a 1. So if I want to pass in a 1, I know what to be it, because if I pass in a 1, it will give -1. So let's put in Z now. So you see, that's the 1. It's going to give minus. So that minus, like I said, the phases doesn't really show in the Bloch sphere. So that minus, you won't really notice it because it's showing you the phase factor, but in magnitude is the same, but in the phase is actually different. So it's -1. But if I reset now and just put Z, it will remain unchanged. So thank God you're following up. So then let's now see the H gate. For the H gate, the H gate has these formulas. So you might just memorize them, but to be sincere, myself, I don't memorize, maybe because I don't memorize them, but it's good to commit them to memory for the sake of mathematics, so you can solve them. so that you can know what it's doing. So the Z gate, the H gate is actually this. One, because if you multiply this into this bracket, it's like multiplying everything inside. That's what it means. I hope it makes sense. You understand that mathematical statement. You understand what this mathematics means? It means this 1 root 2 is going into the whole square. So it's almost like, let me just make it clear. Let me make it clear so you don't get confused. It's almost like this is the H gate. By this scalar. If you use your calculator, you get a fraction, a decimal fraction, a decimal number which you can use. So what it's saying is you multiply it in through. You're having 1 over root 2, 1 over root 2. So this is what it means in 4 minus 1. Does that make sense? Anybody understand what this is? Good. So do you people get this? Do you get the concept here? So let's see. No, that's the H gate. So let's do H. So when you have if you pass in a 0, you will get in a probability of. So this is what this expression means. That's it can either be a 0 or a 1. So the H gate introduce that superposition concept of the Q. So you can see. And we know that this means that it can either be a 0 or a 1 with a probability of 50-50%. So the probability is either a 0 or a 1, and with a phase angle of 0. Okay. So let's now say I want to pass in a 1 to H. What can I do? I think one of you have already answered. I'll first pass an S gate. So the S gate will make it now a 1. If I pass a H gate, so you see what happened? It's on the other direction, telling us that it's negative this. You see that? How many of you understand what is happening here? Because when you put in the X, it's like what is coming out. Let's do backs. When you put in the X, what is coming out is a 1. So it's like you are passing a 1 bit into the H gate. If you pass a 1 bit into the H gate, according to as you see here, it's going to become a negative. So this is this one on this axis. This is the negative here. So let's pass in the H. See? Not on this side. So now that makes sense. Then we have the S gate. Okay. So that playgrounds help you to validate all these. In short, this is the formulas that make up the playground. So it makes it just for you to visualize what really happens when you use a gate. So for the S, the X is defined like this: 1, 0, 0, I. So if you pass in a 0, it's going to be 0. If you pass in a 1, it's going to be IJ. I know this I will not reflect in this sphere, but it's showing a phase factor is present. So let's look at that. If we pass in a 0 using the S gate, it's still a 0, didn't change. If you want to pass in a 1, we put it an X. and put in an S. So you still give 1. You see that? The I is just showing a fifth shift. How many of you understand what is going on? If you understand, just put your hand up high so I can be sure, you know. Do you really get what is happening here?
See, 1, 2, 2.5, 3. We got 10 people. Well, you take away us, 8 people. It looks like the majority of the people.
So I'm guessing the majority understand what is happening. If you don't understand, it's not crime in not knowing. Just say, I don't get what is going on here. Okay. So that's good. So let's go to the T gate. T gate kind of weird. T gate is kind of weird. So let's look at what T gate does. So the T gate is this matrix. Like you need to know why. What is the use case? Did I explain the use case of quantum computing? So there's GPU processing and there's quantum processing. Quantum processing is not the same as GPU. In GPU, you have parallel streams, so a single input, multiple data stream. So you have a single this thing using different threads in parallel. And that's how GPU processing works. But quantum is more like the bits itself can exist either as 1 and 0. So there are cases where quantum computing is very, very good, especially in some medical research, some processing that it shows stronger strength. So that's why it's not like that. So let's see what the T gate is. The T gate is this matrix. One, 0, 0, e raised to the power I pi over 4. That's what the T gate is. And for the T gate, when you apply a 0, it's still 0. So this playground helps you to just see how everything is behaving. So cool. NVIDIA is such a nice company for designing such a playground. So if you put in the T gate, you can see when you put in 0. And if you try the multiplication here, manually, you will see that what we are saying is this is what 0 is. This
So
is what
Daniel,
1. So,
I have a question that came through. I just want to clarify something.
okay.
So basically, quantum computing is linear algebra operating on vectors in the Hilbert space, right? And a qubit is a vector. The Bloch sphere, which is what you're showing, is a visualization of that vector. And quantum gates are matrices that rotate on that vector.
Exactly, correct. Did that question come from a student? I would be so glad if that's a student.
I added a little bit. We combined our brains for the question, but that's basically it.
Okay. Yeah, thank you very much. Yeah, so that's great. So if you try this now, when you give passing a 0, you're gonna get a 0. If you're passing a 1, you're gonna get this. Let's see the T gate. So T gate 0, 0. I want to pass in a 1 means I'll add an X. So it will be 1 the T gate. So it's still, because that magnitude is almost negligible here, it still looks like a 1. This is very interesting. So now we're going to learn what we call Bond's rule. You can be playing with the Bond's rule.
Hold on, Daniel. Daniel,
Yeah.
hold on. And this is very important. I want to make sure we're good on time because there's only 7 minutes left. But this is a quite important rule. So can people stay open maybe 5-10 minutes?
Okay. Yeah.
Yeah.
Run it, and then we'll see where we're at. Go ahead, Daniel.
Okay. You said sorry. I didn't get you. Come again.
No. I was just checking on time for everybody.
Okay. Yeah. We have like 7 minutes. Oh.
Yes.
Oh, sorry. So I'm gonna quickly do this exercise. Then please make sure you go through the GitHub. Very important. Then bombard me with questions. I'm not seeing you guys question on the Discord.
We're about to start, and we apologize for you setting it up and them not taking advantage.
Yeah, please bombard
Can you
the
put it-
Discord with
Can you put
questions.
that in the chat as well, please?
Yeah,
If you have it available.
the GitHub. Yes, I've put it on the chat.
No. The Discord.
No. I have to send it.
If
So you
not,
can
we'll email it. Don't worry about it.
Yeah, so please bombard, don't pity, just any question. I don't know what this is. I don't understand how to do like any question. I'm trying to create my GitHub account. I don't know how to create it. That's kind of question I want to be seen on the Discord. Okay, I'm trying to install Linux. I don't know how to go about it. I'll send you everything you need quickly. That's just what I want to need, because that's the way I will know that you are engaging. You understand? So let's go to the bonds. So I'm going to wrap up with this exercise because of time, and I need to also sleep. It's around 12 midnight. Now it's got 6 minutes.
Thank you,
to 12
sir.
midnight.
Thank you, sir.
It's about 6 minutes to 12 midnight here. So let's understand. Bonds rule is one of the simplest. You will like this one, trust me. It's so we do that visualization. You will love this one. I can guarantee you. This is so interesting. In short, as I was just going through it today, I was so excited. Okay. So we have finished that. I think we'll stop at this. Let's just do this bonds through, then we'll close for today because of time. So bonds rule is the probability of getting a 0 or a 1. So it's denoted by P. Probability of 0 is alpha square. Probability of beta is probability of measuring 1 is beta square. So let's get on that quickly. So let's understand what is happening. So in Bond's rule, the Bloch sphere is the position of where the bit lies on. So you have theta. Let's see. So the formula is this. Let me just get out the formula out for you so that you can. We have 4 more minutes. Anyway, we stop. We just close it for today and continue the next time.
And while you're erasing, I want to try to set up another call too. I know you guys have spring break next week, so it's got to be the week after that. But I think we should get in another session before a video comes, maybe even 2.
Yeah. So
you've covered most of what they wanted on this call.
So this is the formula for this. Take note. Alpha is. I will send you this material on the Discord. This is theta over 2. They're just formulas. So once you know them, beta is actually e raised to the power I theta times sine theta over 2. So, but most times this side is always negligible. So the probability of getting a 0 is always the same as alpha square. Probability of getting a 1 is always beta square. So there are some exercises which I stated you should do. So if I send them, I think I will just close here because of time. So I will send this material quickly to this group. There are some exercises you should do. Exercises, just go through the exercise, which are here, and the solutions are there, explaining why it is. So you did the exercise together with the link here. So you click the link. Task A, apply the H-gate once. Where does the vector space move? Record. So just a task. Take note of things. Then the explanation will be in the solution, why that is. So once you do these exercises, a lab exercise, you will be fine. Trust me. You'll be a master of quantum computing. I think that's what we'll close for today. Yeah.
Fantastic.
Yeah, thank you.
Fantastic material.
Follows I'll send the material quickly. Follows, I just prepared this. I think that was today. So follow the material. I would advise just stick on the exercise and follow it through. You will, and have any question, let me know. So the way you use it is you use this link, copy it, paste it, try it, follow what is done, observe, then go to the solution and understand what is happening. Okay, so that's it for today. Thank you.
Thank you.
Thanks, gents.
Thank you.
Enjoy spring break. We'll talk again very, very soon. Fantastic material.
Yeah,
guys.
yeah.
Fantastic.
See you.
Yeah,
Thank
bye.
you.
Do I get off this? My stuff is has time.